ఓకేనా మ్యామ్?
ఓకే, నేను ఇప్పుడు ఆఫ్ చేసేనా మళ్ళీ ఒకసారి జస్ట్ చెక్ చేసుకోవడానికి.
రికార్డింగ్ అయిపోయింది.
దివ్య మీరు కూడా జాయిన్ అయితే కోహోస్ట్ చేసేసి నేను వస్తాను అక్కడికి.
మ్యామ్ బెటర్ మీది కూడా ఆన్ చేసి రండి మ్యామ్.
నేను ఆన్ లోనే పెట్టాను, సిస్టమ్ ఆన్ లో ఉన్నారా?
నన్ను చేసే మళ్ళీ చేస్తాను.
పార్టిసిపెంట్స్ లో లేరు మీరు?
మ్యామ్ సారీ
మేడం, నేను ఆఫ్ చేస్తాం మేడం ఒకసారి.
ఓకే మ్యామ్ కన్నింగ్ వస్తుంది.
ఓకే ఓకే, అయితే నేను ఇప్పుడు ఆఫ్ లో పెట్టేస్తున్నాను. Yes sir, we can see the screen sir.
Okay, very good. Yeah. Okay, so
yes, everything okay sir?
Okay, so when will you start?
Within just 2-3 minutes we'll start sir.
Okay. Should I put the full screen mode? What is it? This is fine.
No, so put it in this slideshow mode. When you're starting, and put this slideshow mode.
Okay. Comfortable with this? Also?
They cannot, like some font will be small. When it's starting, I will put into select.
Yeah, okay. Well, are things ready? Are you ready to start?
Srividya, are you there? Hello, Srividya. Hello.
Yes, ma'am.
Okay. Okay. Thank you.
Is
Good
it audible,
afternoon,
ma'am?
sir. Yes, it is audible. Thank you. Good afternoon, sir. I welcome Professor V.Sampath, sir, Department of Metallurgical and Materials Engineering, Indian Institute of Technology, Madras. Sir is giving us talk on smart materials, its fundamentals and applications. I request Srividya to introduce Professor Sampath, sir, to us.
Good afternoon, sir.
No.
Before starting this session, let's have a brief information about our today's speaker, Dr. V. Sampath, sir. Sir pursued his ME and PhD degree from Indian Institute of Science, Bangalore, holding top university rank. Sir has more than 33 years of teaching and research experience. He is presently Senior High Academic Grade Professor of Metallurgical and Materials Engineering at IIT Madras. His research interests are shape memory alloys, smart materials, and composite materials and structure property correlation in materials. Sir has received many awards and honors like Bharat Vikas Award 2017, Vidya Bharati Award 1981, the Best Paper Award, and also received first prize under category of transmission electron microscopy in the metallography contest at 73rd annual technical meeting of the Indian Institute of Metal at Thiruvananthapuram 2019. He has guest edited a special issue of Smart Materials of Springer Journal in 2021. Sir has published more than 150 papers in very reputed national and international journals and conference proceedings. Sir has guided many BTech, MTech, MS, PhD, and postdoctoral researchers at national and international level. Sir has undertaken many sponsored research projects and also consultancy projects. He is also life member of the Indian Institute of Metals, the Material Research Society of India, and the Powder Metallurgy Association of India. Sir is presently writing two books, that is Smart Materials and Material Science. He is also reviewer of many journals like Smart Materials and Structures, Acta Materiala, Material Science and Engineering A, Journal of Alloys and Compounds, etc. We are very delighted to invite you, sir. Welcome.
Yes, sir.
Over
Thank
to
you.
you, sir.
Thank you. Well, what's the time given to me?
Sir,
How
1
long
hour
should I
30
talk?
minutes. 1 hour 30 minutes.
30
1
minutes.
hour 30 minutes. Sir.
Okay. Okay. Thank you.
Before.
Well, okay. Okay. Let me start. First of all, thank you so much for this opportunity to deliver a talk to college teachers. And it's a proud privilege for me to deliver such a talk to the college teachers. And so a very good afternoon to you all. And so here we go. So this afternoon, I'm going to talk to you on the topic of smart materials. Now, in the context of smart materials, I'm going to discuss the principles, the mechanisms, and applications. I am Sampath. I'm presently a professor of metallurgical and materials engineering at IIT Madras. So I've been working on smart materials for many years now. In particular, I've been working on shape memory alloys, in particular on nickel titanium shape memory alloys, copper based shape memory alloys, iron-based shape memory alloys, and so on. And many of my doctoral students have been working on nickel titanium, iron-based, and copper-based shape memory alloys. Now, as far as this particular talk is concerned, I'm going to give you an overview of smart materials. That means I will not confine myself only to shape memory alloys, but rather I will give you a bird's eye view of different shape memory alloys. So there is a gamut of shape memory smart materials. So I would like to give you an overview of smart materials in general. So as I said earlier, I'm going to discuss this from the points of view of the principles, the mechanisms, and the applications. So as we go from one smart material to the other smart material, the principles are different, and so are the mechanisms. Now, when it comes to the applications may be met by one smart material and another smart material, and so on and so forth. That means when it comes to the field of applications using smart materials, you can think of not only shape memory alloys, but also piezoelectric materials, macrobiological fluids, and so on and so forth. So let me give you an introduction to the field, to the subject of smart materials. Now, as far as the term smart materials is concerned, in this context, a number of terms are made use of. Many terms are made use of to refer to smart materials. For example, apart from smart materials, intelligent materials, active materials, adaptive materials, actuator materials, sensor materials. And you'll find in the literature and in the books that these terms are used interchangeably. But it should not be done this way, because adaptive materials are different from active materials or intelligent materials. Now, when it comes to the attributes of these materials, please understand that materials have a memory, materials have knowledge, and materials have intelligence. Now, as you go from one material to the other, the attributes are different. The memory levels are different. The levels of intelligence are different. And some materials have physical attributes, and some materials have mental attributes. For example, the word adaptive actually refers to the physical attributes. When it comes to the use of the term active materials, this particular term refers to the mental attributes. Nevertheless, what I want to impress upon you is the fact that in the literature on smart materials, these terms are used interchangeably, but in reality, it should not. I mean, to speak the truth, it should not be done this way. Now, when it comes to smart materials, you find that there are other relative terms such as smart devices, smart systems, and smart structures. So as you find here, the word smart, the term smart is used in conjunction with number of other adjectives or number of other nouns. For example, materials, devices, systems, and structures. Now, as you go from smart materials to smart devices to smart systems and to smart structures, the complexity increases. In fact, you'll find that smart materials form the basis of smart devices, smart systems, and smart structures, and so on. So let us delve deeper into the subject of smart materials. First of all, let me give you an introduction to materials. Let me give you the formal definition of materials. The first bullet says that materials are substances of which something is composed or can be made. And now, as far as this particular talk is concerned, it revolves around smart materials. That means advanced materials, materials which have some unique properties. Smart materials are also called functional materials. Smart materials are also called intelligent materials. So they have a memory, they have intelligence, they have knowledge, so they can act according to the situation. Now, you'll find that materials and systems and structures are different on length scale. So in this context, it will go back to the earlier slide. So you find that as far as this particular subject is concerned, these are the adjective and subject combinations used: smart materials, smart devices, smart systems, and smart structures. And as I said earlier, the smart materials form the basis of smart devices, smart systems, and smart structures. And referring to this particular bullet, you find that materials and systems and structures are different on the length scale. So we'll delve deeper into this. Now, coming to the difference between smart materials and traditional materials, or smart materials and conventional materials. So let us look at the attributes or the characteristics of conventional materials. So in the context of conventional materials, I can say these things: that they are mostly inactive, and that they respond to the environment in a passive way. And they also exhibit properties that are dependent on the environment. So these are in direct contrast to the characteristics of smart materials. Now, what are the characteristics of smart materials? So in contrast to conventional materials, the smart materials are active. They're active. And secondly, they have the inherent capability to interact with and respond to the environment. So in other words, these are responsive materials. These are responsive materials. So they interact with and respond to the environment. And thirdly, the properties are not dependent on their environment. As I said, smart materials are advanced materials, smart materials are special materials, and smart materials are emerging materials. And they are used or they are chosen for different applications, not based on the conventional mechanical and physical properties. They are chosen for their unique properties. For example, if you take shape memory alloys, they exhibit the behavior of shape memory effect. They also exhibit the behavior of superelastic effect. So shape memory alloys are chosen not for any mechanical property, and not for any physical property, but for this special property. It is also sometimes referred to as the functional property. Functional property. So smart materials have certain unique properties, some special properties. So definition, the formal definition of smart materials: these are functional or active materials that have the unique capability to interact with and respond to their environment. So this is their uniqueness, that they can interact with and respond to their environment. Now, when it comes to the surroundings, when it comes to the environment, you can think of different stimuli, different driving forces. The word stimuli is the plural form of the word stimulus. So as far as the environment is concerned, you can think of different stimulants, many stimulants, or many stimuli. And so smart materials have the ability to interact with and respond to the environment. And the environment can have these things to offer: maybe stress, temperature, viscosity, magnetic field, electric field, light, and so on. So these could become a part of the environment. So it may, of course, vary from one situation to the other. Smart materials. There are 5 different characteristics of smart materials. What are these? Smart materials possess some unique properties. Unique properties. For example, in the case of shapemer alloys, you can think of shapemer effect. You can think of superelastic effect. Now, in the case of piezoelectric materials, you can think of piezoelectricity, okay, and so on and so forth. So they possess certain unique properties. They offer certain unique properties. And secondly, they possess intrinsic and extrinsic capabilities to respond to stimuli and environmental changes. Intrinsic and extrinsic capabilities to respond to stimuli and environmental changes. And thirdly, it is a very important point, and most smart materials respond with a change in shape upon application of externally applied driving forces. Just now, we looked at the fact that we can think of different stimulants, we can think of different stimuli, and most materials interact with the stimulant or the stimuli and give rise to a change. And this change is mostly in terms of a shape change. It need not always be a shape change, but by and large, the change that is given rise to is in terms of a change in shape. And fourthly, the change occurs by design. Very important. So this is to be noted. This change, the change in shape, or whatever may be the change that occur, doesn't occur by chance, but by design. It doesn't occur by chance, but it occurs by design. And finally, the magnitude of change is appreciable. It is not that it is not perceptible. It is not that it is not noticeable. In fact, the magnitude is such that you can notice it, you can observe it, you can record it. Okay, so these are the things pertaining to smart material. Magnitude of change is appreciable. And let's move on to the definition of structure, smart structure. So when it comes to a smart structure, it is an aggregate of parts as dominated by the general character of the whole. So there are different ways of defining a smart structure. There are different ways of defining a smart structure. Rather, there are different characteristics of a smart structure. So these are brought out by these bullets. First, an aggregate of parts. And secondly, a smart structure is something that is arranged in a definite pattern of organization. And if one strictly follows the dictionary definitions, then clearly intelligent, smart, adaptive, etc. are different adjectives altogether. So these are all adjectives: intelligent, smart, adaptive, active. Okay, so they bring out the attributes, they bring out the characteristics of the material. But the word that is used should be the right one, and it should represent the material's true behavior. So we have so far defined smart materials. We also define smart structure. Let's move on. Now, coming to the classification of smart materials, we can think of different smart materials. So what I have given you here is only a very short list. Piezoelectric materials, magnetostrictive materials, shape memory alloys, optical fibers, electrochromic materials. So list is by no means exhaustive. It is only a small list. Okay. But what is the common thread that is running through these materials? So these are all smart materials. But then what is common among them, and what are the differences that exist among them? So first and foremost, a smart material receives an input and gives rise to an output. Receives an input and gives rise to an output. Let me, for example, take the example of shape memory alloys. Shape memory alloys are also called thermo-responsive material. Why are these called thermo-responsive materials? The reason is that in the case of shape memory alloys, the shape change, okay, is given rise to by a change in temperature, or the material or the device goes back to its earlier shape upon heating. In other words, temperature plays a major role. So in the context of smart materials, we have so far been talking about the driving forces. The driving forces. Now, if you look at these smart materials, you'll find that as you go from one to the other, the input and the output are different. Take, for example, piezoelectric materials. In the case of piezoelectric materials, the input is stress or load, okay, and the output is potential, voltage, okay. So this is as far as the piezoelectric materials is concerned. Now, if you take electrostatic materials, in the case of electrostatic materials, the input is an electric current and the output is a change in length. In the case of magnetostatic materials, it is slightly different. So instead of an electric current, you can make use of a magnetic field. So a magnetic field can give rise to a change in length, a change in shape. So what I want to drive home here is that as you go from one smart material to another smart material, the input and the output are different. In other words, the driving force and the outcome are different as you go from one smart material to another smart material. So here is a short list which gives you the stimulus response list. Stimulus response list for different smart materials. And even though there are many smart materials, some are chosen mostly for sensor applications, whereas certain others are chosen for actuator applications. I'm sure you know the difference between a sensor and an actuator. A sensor is one which senses, okay, whereas an actuator is one which does some work, okay. So even though we have different smart materials, some are chosen to be used as sensors, whereas certain others are chosen to be used as actuators. Okay. So this is a list, which actually correlates the input and output in different smart materials. Okay. Again, looking at the stimulus response matrix for some select smart materials. So let us look at the table. So this actually correlates the response to the stimulus, or the stimulus is, that is the input, is correlated to the output or the response. The response is different in different smart materials. So if, for example, the stimulus is electrical and the response that is given is related to some optical properties, then you can think of such materials as electrochromic materials, electroluminescent materials. electro-optic materials. Okay, so this is in other words, you are able to understand the difference between the stimulus, the driving force, which is electrical, and the response, which is optical. Take, for example, the electrochromic materials. So you know the meaning of chromic, okay? Chromism. I'm sure you are familiar with the word chromic or chromism. Okay, electrochromic materials are those materials which undergo a change in color in the presence of an electric field. Okay, next one, thermal. Okay, so the stimulus is electrical and the response is thermal, and such metals are called thermoelectric. And so that means when a material is heated, so when a material is subjected to an electric current, or when an electric current is passed through a material, the temperature changes. So this is the meaning of saying thermoelectric. Then piezoelectric. So I'm going across, across the columns. So electrical or electricity is the stimulus, and the response could be in the form of electrochromism or thermoelectricity or piezoelectricity. Okay, I think instead of spending much time on this, I will move ahead because the subject is very, very vast. There are a lot more things to be taught and learned. Okay. Now, functions of smart materials. So we have looked at different smart materials so far. We looked at piezoelectric materials. We looked at shape memory alloys. We have looked at electrostatic materials and so on. So what is common among them? So if you consider the smart material as an active material, in fact, smart materials are also called active materials. Okay. Now, what are the characteristics of smart materials? First and foremost, they act as transducers. They act as transducers. That means they convert an input and into an output. Convert an input into an output. In other words, they can convert one form of energy into another form of energy. So the input is also known as stimulus, driving force, whereas the output, okay, is also called response. Okay. So we have come across many smart materials so far, and you have noticed that the input and the output are different as you go from one smart material to another smart material. Now, basis of classification of smart materials. How are smart materials classified? Well, the principle that is used, or the criterion that is used, is based on the input and the output. That is based on, you know what it is, the stimulus and the response. Based on the stimulus and the response. So here are a couple of examples. The input is change in temperature, and the output is a change in magnetic field. So I can think of shape memory alloys. So in the case of shape memory alloys, when there is a change in temperature, it gives rise to a change in shape. Now, in the case of magnetostrictive materials, a change in magnetic field can give rise to a change in length. Now, input is this, then output. The output could be different, okay, as the case may be. So the output could be in the form of a change in length. It could be a change in viscosity, or it could be a change in electrical conductivity. So, for example, in the case of shape memory alloys, the length could change, or the shape could change, or the volume could change. And in the case of some materials known as magnetorheological fluids and electrorheological fluids, there occurs a change in viscosity. There occurs a change in viscosity with respect to the application of either an electric field or a magnetic field. Similarly, the output could be in the form of a change in electrical conductivity. So this is as far as the basis of classification is concerned. Now moving over to smart system. So we have said earlier that the word smart, or the term smart, is associated with a number of terms: smart materials, smart systems, smart structures, and so on. Now, what about a smart system? A smart system senses and responds to its environment, and a smart system incorporates many components. For example, maybe an actuator, a sensor, and the central electronics. Now, smart system, a formal definition. There are different ways of defining a smart system. So here we go. A regularly interacting interdependent group of items forming a uniform whole. A smart system may refer to a group of items, or there's another way of looking at it, an assemblage of substances that tends towards equilibrium. And the third way of looking at it is a group of devices or artificial objects, or an organization forming a network. This is the third way of looking at a smart system. But nevertheless, what is driven home is that this emphasizes a collective of components working towards a common purpose. So it means, so you have an assemblage of substances, or a group of items, or a group of devices. So they all have a common goal, a common purpose. So which implies that individually the components have different purposes from that of the collective. So individually they may have different purposes, different objectives, but collectively they have a common goal. Collectively a common goal. And that is what is being served by what is known as the smart system. So this figure actually brings home the interplay of different disciplines. Smart materials and systems occupy an overlapping technology space between sensors and actuators and functional materials. So here is where smart materials and systems is. So this is one domain. So this is an overlapping domain between sensors and functional materials and actuators. And it also has a strong bearing from nanotechnology and biomimetics as underpinning technologies. So we have so far looked at smart materials, smart systems. Now let us look at smart structure. What are the components of a smart structure, or what are the functions of a smart structure? I can see 5 different functions, or rather a 5-fold function as far as a smart structure is concerned. A smart structure, because a smart structure usually incorporates a sensor or maybe a group of sensors, an actuator or maybe a group of actuators, and the control unit. And between them, data transmission can occur. That is between the sensor and the control. Similarly, data instructions could occur or take place between the control unit and the actuator. So I can say that there is a 5-fold function with respect to any smart structure. First, sensing. Second, data transmission. Third, actuation. Fourth, data instruction. And fifth, controlling or control. So these are the 5 different functions of a smart structure. Here is a practical smart bridge. The smart bridge incorporates many smart elements, many smart materials. Now, for example, you can make use of conventional strain gauge, PVDF, PZT, optical fibers, and so on. I'm sure you're familiar with PVDF. It is a piezoelectric material. That means when you apply stress, it gives rise to a potential difference. It is a polymeric piezoelectric material, PVDF. Similarly, you can think of PZT. It is again a piezoelectric material, but then it is different from PVDF in that it is a ceramic piezoelectric material. In fact, piezoelectric materials are popularly known as the PZTs. Okay, that is the lead. What is the expansion for PZT? So it is the abbreviated form for lead, zirconate, and titanate. Lead, zirconate, and titanate. It's a complex, a combination of different oxides, lead oxides and zirconium oxide and titanium dioxide. So it is a complex combination of different oxides, but it's a very popular piezoelectric material, and the PZT fibers are especially used in sensing and also in actuation. So when it comes to a smart bridge, these materials are made use of in different areas. So you have the pillar here, you have a pillar, and it has attached or embedded sensors. And then here, okay, as for the foundation of the pillar is concerned, there are the actuators and LVDT. And beneath the bridge, there are actuators and sensors. So why should you make use of these materials or smart materials in a bridge? We should incorporate the smart material or the smart elements in a bridge for many reasons. First, now we want the bridge to be healthy. Okay. Let's say there is a bridge which was built some 50 years ago, okay, and it's been in constant use. We would like to know the state of health of a bridge. We want to know if any flaws have crept in, any defects have been formed because of constant usage. So all this is possible by using these smart materials. these smart elements. Okay, so we will know the exact location where the flaw has been initiated, the flaw has been formed. We will also know the extent to which the flaw or the defect has been formed. And it is also possible to predict the remaining lifetime of a bridge. It's very, very important because we do not want any bridge or any building for that matter to collapse catastrophically. That means without any warning. So we like to know the remaining life period. So in fact, there's a field which is called remaining life prediction. So there are theories concerning the prediction of the remaining life of a bridge. In fact, it is very, very important because by giving credence to such theories, such a concept, so you can safeguard yourselves from danger. You can protect the bridges from catastrophic failures. So actually, so these smart materials are helpful in knowing the state of health of a bridge. So this is called health monitoring. Health monitoring. So we like to know the state of health of a bridge. So that's why we incorporate these smart elements or these smart materials in a bridge. Once you incorporate these smart elements in a bridge, it becomes a smart bridge. Okay, now different parts of a smart bridge. I don't want to spend much time on this, but then you have the main portion, the bridge deck. So this refers to the top surface of a bridge which carries the traffic. The second important part is the pile. It's also called a long column driven into the ground to form part of a foundation or substructure. The third one, the girder. So this refers to a horizontal structure member supporting vertical loads by resisting bending. The girder is basically a larger beam, and especially when it's made of multiple metal plates, the plates are riveted or welded together. So we can look at the smart bridge once again. So this is the bridge deck. Okay, this is a bridge deck, and so this is the exploded view of the bridge deck. So as you can see here, steel stroke FRP reinforcement and fiber optic sensors. So here is the fiber optic sensor. It's an optical fiber. And second one, this one, which we have already seen, that is the pile, long column. So you have actuators and LVDT. Let's move on. Now let us look at an aircraft. The aircraft is a perfect example for a smart system. But please note that an aircraft is not a stationary structure, but a mobile structure, or is a mobile system. And it has different parts, and in different parts, you make use of different smart materials. And these smart materials have different purposes to achieve. Okay. So there are at least 5 different areas where you can make use of smart materials or smart systems. For example, in the central control unit, and then in cabin noise reduction. Third, flutter suppression or flaps positioning. Fourth one, engine monitoring. And fifth one, vibration damping impact reduction. So you find that there are 5 different areas. In these areas, smart materials are made use of. The subject is very vast and time is very short, and I'm not able to explain all the things that are required here. So I'll move on. Smart structure material system. So what does a smart structure or a smart material system incorporate, which we have already seen? First and foremost, you should have sensors and actuators, integrated sensors and or actuators. Second, the ability to sense its environment and respond in a beneficial and controlled manner. And the third one, processors or electronics or basic materials response capabilities to produce a designed motion or effect. So these three are very much required or essential in the context of a smart structure or a smart system. Application of smart materials. Smart materials are used in diverse fields, in many fields. So here is a short list, but we can just pick some of them, but some important areas: transportation, healthcare, construction, okay, then energy and environment, space, defense, and so on. So in many areas, you can make use of smart materials. Now, coming to smart systems for engineering applications, what are the general requirements and expectations of smart systems? So many are listed here, at least 5 different points are listed here, but I shall highlight some of them here. First, there should be high degree of reliability, efficiency, and sustainability, not only of the structure, but also of the whole system. Reliability, efficiency, and sustainability. And second important point, high security of the infrastructures, particularly when subjected to extreme and unconventional conditions. Very important. You may not be able to predict what may occur at the next moment. Okay, we may not be able to predict the forces. We may not be able to predict the environment. And especially when they're subjected to extreme and unconventional environments or conditions, the metal or the system or the material may not do so well. So from that point of view, it is very important. High security of the infrastructures, particularly when subjected to extreme and unconventional conditions. Fourth one, continuous health and integrity monitoring. So a short while ago, we looked at a smart bridge. The smart bridge incorporates many smart elements, many smart materials. So these materials are incorporated in different areas or in different parts of a smart bridge for definite purposes. So as I said initially, that in the case of a smart bridge, you incorporate the smart elements or the smart materials with a view to knowing the initiation of a flaw, the initiation of a defect. Okay, once you have incorporated these elements, you will know as to the exact location where the particular flaw has been initiated. And secondly, you will also know the magnitude of the flaw or the defect that has been given rise to. And thirdly, once you have known the nature of the flaw and the location of the flaw, you'll be in a position to extrapolate. You'll be able to predict the remaining life period of a smart material, of a smart bridge. So for continuous health and integrity monitoring, smart systems are really helpful. And another important part, damage reduction and self-recovery. Damage reduction and self-recovery. So in some smart bridges incorporate some smart materials, and they have the tendency to heal themselves. It's called self-healing. It's known as self-healing structures. There are self-healing materials. There are self-healing structures. So there is something known as self-healing cement in civil engineering. So if that flaw has been given rise to, the metal has an innate ability to heal itself of the defect, to heal itself of the flaw, so that the health is maintained. So self-recovery. And to do these things, we need to think of the appropriate smart technologies. What are the smart technologies that are required? What are the different aspects that we need to think of? One, new sensing materials and devices, new actuation materials and devices. And third, new control devices and techniques. Very, very important. That means from the point of view of sensing, from the point of view of actuation, from the point of view of control, we need appropriate devices, appropriate material. Please note that when we started discussing, we looked at the 5 different functions of a smart structure, or the 5 different characteristics of a smart structure, namely sensing, actuation, control, data transmission, and data instruction, and so on. So to achieve these things, we do need appropriate materials and devices. So the first 3 points are related to what you have seen earlier in the context of a smart structure. And fourthly, self-reduction, self-diagnostic, self-correction, and self-control functions of smart materials and systems. It's a very, very important field. Self-correction and self-diagnosis. Self-diagnosis, self-reduction or self-diagnosis, and self-correction and self-control. So all this is possible. So now engineers and technologists are entering into this exciting area. Now coming to the classification of smart materials. Smart materials can in general be divided into 2 different types, namely group 1 and group 2. What are the characteristics of group 1 smart materials? As far as group 1 smart materials are concerned, they respond with a change in shape and a length of an application of a stimulus. Excuse me. They respond with a change in shape and a length upon application of a stimulus. And the input is always transformed into strain. And thirdly, the strain is used to introduce motion or dynamics into a system. So please note that there are many characteristics with respect to group 1 smart materials. First and foremost, they respond with a change in shape and a length upon application of a stimulus. You know the meaning of stimulus, the driving force, that is the input. So the input gives rise to an output. So the output is always in the form of a shape change or a change in length or strain. And the strain is used to introduce motion or dynamics into a system. And group 1 smart materials are by and large used in the design of smart structures. They're mostly used for the design of smart structures. For example, they are integrated into mechanical host structure. Here are some specific examples: buildings, helicopter rotor blades, and so on. Even though they are by and large used in small structures, they are mostly used as actuators. That is, their main function here in a small structure is to function as an actuator. But be that as it may, sometimes these materials can also act as sensors when a strain applied to the material is transformed into a signal that allows computations of the strain levels in the system. It is possible both ways. A sensor can be used as an actuator. Similarly, an actuator can be used as a sensor by reversing the direction. By reversing the direction. So these are the characteristics of group 1 smart materials. Please note that the output is always or mostly in the form of a shape change or a change in length. And they are mostly used in smart structures. Now moving over to group 2. These are in contrast to group 1. They respond to stimuli with a change in key material property, not a change in length, not a change in shape, but a change in key material property. So you can think of such properties as electrical conductivity, viscosity, and so on. And unlike in the case of group 1 smart materials, which do find applications as actuators, you generally find that group 2 materials are by and large used as sensors. In other words, they're less frequently integrated into mechanical structures. And they're mostly used to design complex modules such as clutches, fasteners, valves, and various switches. Sometimes called actuator systems. Materials coming under group 2 are sometimes called actuator systems. For example, you can think of electro-rheological fluids and magneto-rheological fluids. Because in the case of an electro-rheological fluid, you find that when an electric current is passed into the fluid, the viscosity changes. The shear modulus changes. So as we've seen already, as we see just now here, that there is no change in length, neither is there is a change in shape, but there's a change in key material property with respect to the application of a stimulus. Okay, the stimulus in the case of an electrorheological fluid is an electric field, and the output is the change in viscosity. A similar thing can be observed in the case of the magnetorheological fluids also. So instead of an electric field, you can also think of applying a magnetic field. This again brings about a similar result. For example, a change in viscosity, but it is in the presence of a magnetic field. Such fluids are called magnetorheological fluids. You know the meaning of rheology, okay? Rheology related to viscosity. So viscosity changes are introduced either by an application of an electric field or a magnetic field. So as you can see here, these fluids respond with an increase in viscosity upon application of an external electric or magnetic field. Now we come to an important point, and that is, depending upon the stimulus response direction, a smart material device can be used as both actuator and sensor. They can be used as actuator and sensor. Having seen the characteristics of smart materials, smart systems, smart structures, and having looked at the classifications of the smart materials into group 1 and group 2 smart materials, let's get to know the different functions of a smart material. In the context of a smart material, you can think of a fourfold function. First, they receive information. And second, they transmit the information. Third, they process the information. And fourth, they respond to the information. So this is a fourfold function of any smart material. Now, smart materials are a little different from the so-called intelligent materials. They're similar, excepting a shade of difference. In the case of intelligent materials also, you find the fourfold function, that is reception of signal or information, transmission of information, processing of information, and responding to information. So in addition to these characteristics, they also have the ability to take decision, inherent ability to take decision based on the information. So from this point of view, from this particular angle, intelligent materials are a little different from the so-called smart materials. Okay. So now, having given a detailed introduction to smart materials, let us look into some of the smart materials that are more prominent. Okay. So to do that, let us look at the piezoelectric effect. So piezoelectric materials exhibit what is known as piezoelectric effect. Now, the word piezoelectricity can be divided into two, namely piezo and electricity. The word piezo actually has its origin in the Greek language, meaning squeeze or pressure. So when you read these two words together, piezo and electricity, it gives an impression or it gives a meaning of squeeze electricity or pressure electricity. In other words, when some metals are compressed, when metals are pressed, or when metals are squeezed, they give rise to an electric current. They give rise to a potential, and that is called piezoelectric effect. And so, as I said earlier, so piezoelectric effect gives you the link between a metal's mechanical behavior and electrical behavior. What is mechanical behavior and what is electrical behavior? So you apply a load, you apply stress, that is mechanical, and that is the input. And you get an output, that is a voltage, a potential, and that is electrical in nature. So the two are linked. The mechanical and electrical behavior are linked. In other words, piezoelectric effect is a perfect example between is a perfect interface between the mechanical and electrical behavior of a piezoelectric material. Now, as far as this particular phenomenon is concerned, it was first discovered by a couple of French scientists. Hello? Yeah. The phenomenon was discovered way back in the 1880s by French brothers by names Jacques Curie and Pierre Curie. They actually discovered this phenomenon by an accident. Actually, they wanted to study certain behavior of quartz. So they started experimenting on quartz crystals, and what they observed was piezoelectric effect. Now, looking much more deeply into piezoelectric effect, it is electric polarization brought about by mechanical input. Electric polarization. So what gives rise to piezoelectric effect? Piezoelectric effect is given rise to by what is known as the formation of dipoles, polarization. polarization by mechanical inputs. When we say mechanical inputs, I refer to a load. I refer to stress. It is manifest when a material is subjected to a voltage drop resulting in a shape change. Conversely, it develops an electric charge on its surface when squeezed, that is subjected to mechanical deformation. So here is a piezoelectric crystal. Okay, and so when there are no loads applied, or when there is no stress applied, it is not give rise to any voltage. Now, moving over to the figure beside, you find that on application of pressure, okay, on applying a load, the dimension changes. Correspondingly, it gives rise to a voltage. Okay, and this is what is called the piezoelectric voltage. This is what is called the piezoelectric effect. Okay, so a similar phenomenon can occur when the material is pulled in tension. So please note that the piezoelectric effect can be given rise to by a material exhibiting the piezoelectric tendencies not only in compression but also in tension. So look at this, the third figure. So you find that the same piezoelectric crystal, when pulled in tension but not in compression, not compressed, but it's pulled in tension, it does give rise to a voltage. And this is what is known as the piezoelectric effect. Moving a little closer to understanding the mechanism of piezoelectric effect. So piezoelectric effect is given rise to by certain crystals. So it's known as piezoelectric crystals, and some of them are polycrystalline and some of them are single crystals, and each one has its own advantages. Okay, and so in the context of the piezoelectric effect, okay, so I want to bring to your attention what is known as the composition PZT. P for lead, Z for zirconate, and T for titanate. So as I said earlier, it is a complex oxide. Okay, it's a complex oxide, and so they form a crystal, a piezoelectric crystal. And by deforming a crystal, okay, so what really happens is that, so okay, let's now look at the undeformed crystal. Undeformed crystal. So here you find lead atoms occupying the cube corners, the oxygen atoms, occupying the phase centers, and the titanium or zirconium atom occupying the body center. Okay, when such a crystal is deformed, okay, it may be from sideways or from the top. So what happens is that it gives rise to a voltage. It gives rise to a potential. So what is the reason? Let us look at the reason for that in the next slide. So direct the piezoelectric effect. To explain the concept of piezoelectric effect, I must talk about what is known as symmetry and non-symmetry. So you know the meaning of symmetry, a symmetrical structure, the symmetrical crystal, and a non-symmetrical crystal. When you think of a symmetrical structure, you find that the centers of the positive and the charges and the negative charges do not coincide. So when it comes to the crystals, you can think of two different types. One, crystals with symmetry and crystals with non-symmetry. In the case of crystals that are non-symmetrical, you'll find that the centers of the positive charges and the centers of negative charges do not coincide. Fine. What is the result? So this will cause the formation of a dipole. It will give rise to the formation of a dipole. So it is the formation of dipoles. Okay. So this will lead to the production of a net charge on the crystal. And this is the origin of what is known as the piezoelectric effect. So one of the most fundamental aspects of this is the non-symmetrical structure of the crystal, in which the centers of the positive and negative charges do not coincide and therefore form dipoles. So in the absence of stress or external stress, external strain, the charge distribution within the crystal will be symmetric and the net electric dipole moment is 0. So we are talking about the net electric dipole moment. Okay. So in the case of a symmetrical crystal, the net dipole moments will be 0, or the total dipole moments will be 0 in the case of a symmetrical crystal. Okay. So this is the basis of what's known as piezoelectric effect. So we have so far discussed the direct piezoelectric effect. Now moving over to the indirect piezoelectric effect. It is a converse of direct piezoelectric effect. So as the figure here illustrates, when an electric current is passed through a piezoelectric material, it deforms. As far as the direct piezoelectric effect is concerned, we were looking at the application of a load giving rise to a voltage. But here, the converse. That is, you pass a current and it gives rise to the deformation of the crystal. So look at this. So this is a crystal and the circuit is not complete. No current is passed, no deformation. We move over to the right. Now a current is passed into the crystal. It leads to deformation. And this is what is known as the piezoelectric effect. Now let us look at some of the piezoelectric materials. We have already seen that there are many materials exhibiting piezoelectric effect. But the most important thing to note is that the symmetry or non-symmetry is very, very important. If the crystal is symmetrical, it will not give rise to an overall dipole moment, and there will be no piezoelectric effect. Then when the net dipole moment is 0, it cannot be used as a piezoelectric crystal. Okay, so it boils down to one thing, and that is, in the case of cubic crystals, which are symmetrical, there will be no net dipole, there will be no overall dipole moment. And as a result, there will be no piezoelectric current. So that means you would rather prefer a crystal which is non-cubic. Not cubic, but non-cubic. Okay. Now coming to the materials which exhibit piezoelectric effect, these are mostly ceramics and polymers. When it came to the smart bridge, we looked at the fact that PVDF is made use of. What is PVDF? It is a polymer, or to be more precise, it is a piezo polymer, and the name of which is polyvinylidene difluoride, PVDF. It's also called a smart polymer. And then the PZTs, it's a family actually, lead, zirconate, titanate. So you have PZT3, PZT4, PZT5, and so on. So these are different in terms of composition. And then you have barium zirconate, then this one. This is a polymer, polyvinylidene fluoride, and then quartz and Rochelle salt. In fact, the phenomena of piezoelectric effect were first discovered in quartz and subsequently in Rochelle salt. And then they moved on to the compounds such as the PZTs. Application of piezoelectric materials. Piezoelectric is a mature technology with numerous applications. They are used in different areas. In particular, they are used as actuators. What is the role in actuators? I mean, if they are used as actuators, what is it that they do? For example, in controlling chatter in precision machine tools. You know the meaning of chatter, machine tool chatter. That means vibrations, controlling vibrations. Then robotic parts, greater speeds and accuracy. And third one, microelectronics. In such parts as computers and in photolithography printer and in health monitoring fibers in bridges. So this is what I illustrated to you. That is the use of fibers, health monitoring fibers in smart bridges. They are also used in other areas such as adaptive optics and microphones. Properties of PZT. So this table actually brings to light a gamut of properties. But what is more important about the PZT is the strain that it undergoes. Okay, so here, apart from many other properties, the strain is also mentioned. Maximum actuator strain in meters per meter. So whatever may be the smart material, ultimately we like to compare certain properties. There are two things we generally would like to compare. One, the strain, and then force. What is the force that it can generate? And what is the strain that it can give rise to or it can undergo? So these two are the properties. And so as far as the PZTs are concerned, they undergo a very low level of strain. Now, I'm sorry. Yeah, just bear with me for a minute. Yeah. Let's see. So, so now let's move on to electrorestrictive materials. So these are again smart materials. What about the input and the output as far as the electrorestrictive materials are concerned? When it comes to the input, an electric current is the input, and when it comes to the output, strain expansion is the output. That's a change in length of the material in the presence of an electric field. So the word striction actually comes from the Latin language, meaning compression, striction, Okay, so there's a change in length, electrostriction. And so as one of the points illustrates here, these metals undergo a change in shape in the presence of an electric field. Example, lead magnesium iodide. Okay, so they have some attractive properties. For example, possess high relative permittivity and extraordinarily high electrostatic coefficients. And there's yet another important point that is to be noted in the context of the electrostatic materials, and that is most of these electrostatic materials that are used are very brittle. So on the one hand, they undergo less of strain. The maximum strain that they undergo is very less. On the other hand, they are very brittle, but nevertheless, they are still used. And generally, the electrostatic materials that are used are much more costlier. PMN. So this is abbreviation for a particular type of electrostatic materials. Lead, magnesium niobate. Lead, magnesium niobate. It is an electrostatic material, and as far as this material is concerned, the strain is the output, the displacement is the output, and what's the relationship between the strain and the force that is applied? So we generally find that the displacement is proportional to the square of the voltage, the square of the electric current. So here is a plot which actually correlates the strain to the field that is achieved, the field that is applied. So there are two materials that are being compared, two smart materials that are being compared here. One is the electrostatic material. So this one, okay, it shows more like hysteresis. Okay. So this is the behavior exhibited by an electrostatic material with respect to the application of a field, electric field. On the other hand, in the case of the piezoelectric material, this is the kind of behavior that is shown. So this is what we have already looked at. So the most important thing is displacement proportional to the square of the applied voltage. So PMN is the acronym for lead magnesium niobate. It's a very popular electrostatic material, as is the case with PZT, lead zirconate titanate. And as you already seen, the strain behavior with respect to the applied field is different as you go from the electrostatic to the piezoelectric materials. Electrostatic materials are used in a number of applications, but to understand the principles, you find that an electric field separates the positively and negatively charged ions, in the process changing the dimensions of the cell and resulting in an expansion. So this is the secret behind the expansion that you observe. This is the reason behind the change in length that you observe in the case of an electrostatic material. Moving over to magnetostatic materials, these are similar to electrostatic materials. The only difference is that instead of an electric field, you make use of a magnetic field. So in the presence of a magnetic field, the materials show a change in length. So look at the figure by the side, on the left side. So two situations are being reflected here. So this is basically a magnetostatic material, no magnetic field. So it has a specific length. Now, it is subjected to a magnetic field. So what do you see here? You find that the length changes. So a field in excess of 500 Oersted is being applied, and this has given rise to a change in length. So as has been explained just now, these are materials that have the capability to undergo an induced mechanical strain when subjected to a magnetic field. And they are mostly used in actuators, by and large. So we started our discussion by looking at the different classes of smart materials. Some are used in sensor applications, and some are used in actuator applications. But by and large, the macroscopic materials are used in actuators. Of course, they can also be used in sensors, and the reverse phenomenon is called piezomagnetism. The reverse phenomenon is called piezomagnetism. And they are used in many areas: mirror deflectors and MEMS, vibration and noise control, motors, etc., etc. So look at the figure below. Look at the one which I'm indicating now. So here again, in the presence of a field, the magnetic dipoles orient themselves along the direction of the magnetic field. So here, look at this diagram. Here is the arrow. The arrow indicates the direction which the magnetic field is applied. And what about these ellipses? The ellipses represent the domains or the dipoles. Okay, so the dipoles are all oriented along the direction of the magnetic field, giving rise to a change in length. A change in length. There's an example here. For want of time, I'll skip this and then I'll move on to the electrorheological fluids. Okay, so these are also known as ER fluids. Sometimes these are also called smart fluids. Both ER fluids, electrorheological fluids, and MR fluids, that is macrorheological fluids, are called smart fluids. Okay. And as far as the electrorheological fluids are concerned, these are basically insulating fluids consisting of particles dispersed in a liquid. So as far as the composition goes, you have two major components. One, the carrier liquid, and two, the particles. Once again, there are two major components as far as an electrorheological fluid is concerned. One, the carrier liquid, and two, the particles. And the particles are usually magnetic. Okay, they have magnetic behavior. They exhibit magnetic behavior. Okay, and so of the two components, namely the liquid and the particles, at least one of them is semiconducting. Now, in the presence of an electric field, you find that the metal undergoes a change in properties. The rheological behavior changes. Rheology refers to the viscosity. What are the properties that you can think of in the context of the rheological properties? One, viscosity. Two, yield stress. Three, shear modulus. So all these properties undergo a change on exposure to an electric current. And please note that this phenomenon is reversible. And so on the right side, you find two figures, one at the top and one at the bottom. The one at the top actually illustrates the behavior of a typical ER fluid, electrorheological fluid. Let me explain this. So this is the off-field condition. In the context of electrorheological fluids, there are two situations. One is the on-field condition and the off-field condition. So as far as this one is concerned, this is reflective of the off-field condition. That means the material or the fluid is not subjected to any electric field. Now what happens? You find that the particles are all dispersed. Okay, and there is no order. Okay, and in this state, it will exhibit some level of viscosity. Now, this liquid is now exposed to an electric field. Now, what does it cause? It causes the particles to undergo polarization. The particles undergo polarization. So each particle becomes a dipole. Okay. And on continued application of the stress, not the stress, I'm sorry, the field, electric field, you find that the particles align themselves in the direction of the field, giving rise to a fibular structure, a fiber-like structure. So this actually changes the behavior of the material. When I say behavior, rheological behavior, I refer to the viscosity. The viscosity increases, the shear modulus increases, and so is the case with the yield stress. So this is as far as the electrorheological fluids are concerned. Please note that. So this is the off-field condition. Off-field condition, no field. And a field is applied, it causes polarization of the particles. The field is continued to be applied. Now the particles align themselves and also attach themselves to each other, giving rise to a fibular structure, a network of fibers, okay, a network of particles. So this only brings about a large change in the properties. In contrast, you can think of a non-ER fluid. What's the difference between an ER fluid and a non-ER fluid? The difference lies in the fact that here again, you start with the no field condition, but you apply an electric field. So what do you see? Dipoles are formed. But then the next step, that not only should the dipoles be formed, but they should also align themselves along the field and attach themselves with one another. So this capability is not exhibited by the non-ER fluids. So this behavior is actually used in a number of practical applications like clutches, brakes, damping systems in automobiles, robotic hands, robotic arm joints, shock absorbers, and so on. So it's a very, very important field. It's a very important subject. So electrorheological fluids are used in very many practical applications, especially they are used in many devices, for example, in clutches, in brakes, in dampeners, and in robotic hand. These are very important, significant engineering applications. Moving over to the magnetorheological fluids. In contrast to the electrorheological fluids, a similar effect is being brought out in the case of magnetorheological fluids also. The only difference lies in the fact that the input is different. Instead of an electric field, you apply a magnetic field. Okay, so here again, you have a carrier liquid. Usually it is an oil. And then the carrier liquids carries particles, magnetic particles. And in the presence of a magnetic field, you find that the particles form a fibrillar structure, a fiber-like structure. And so in the direction opposite to this one, okay, so this is the direction in which the field is applied. Now the fluid flows in this direction. Now you find that the particles or the fiber structure or fibrous structure is oriented opposite to the direction in which the fluid flows. In other words, this develops a greater resistance to the flow of the fluid. So this is how the change in the behavior of a macrobiological fluid is being brought about. Now I think I should ask the organizers. So Dr. Premalada, please let me know. I think I have not covered much. I have not taught much. I have just discussed a couple of smart materials.
You want, sir? Good afternoon, sir. Sir, you want
Yeah.
to, sir?
Yeah, please come again. Yeah.
Sir, if you want to continue, sir.
Yeah.
Sir, you can, sir. Magnetorheological fluids.
Yeah.
Already this section is discussed by one of our professor, Saraswatama madam, sir.
Okay.
So
okay.
already this was covered yesterday, sir.
Okay. Okay. So then I will. There are other topics. Then I can discuss them.
Yes.
Okay. I can.
Yes, sir. Yes, sir.
I can discuss other topics. All right.
Yes, sir. Sure. Yes, sir.
Okay. 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 So then okay. How much time do I have?
Actually,
Yeah, I've exceeded the time.
It is already 4:10 o'clock.
Madam, better continue. Better continue for some more. Yeah, please ask this sir to extend his lecture some more time. Yeah.
Participants are asking, sir.
Okay.
Actually,
okay.
time is over, but participants are interested.
Okay, fine. So, yeah, I'm
Please
only
carry on, sir.
Okay, thank you so much. But I'm only halfway through. Many more slides to come. And so, as far as macrobiological fluids is concerned, you have already been taught. You've been already given a lecture, right?
Yes, sir. By one of our professors, she has given.
Okay. So in that case, I will move on to other topics. I'll continue. Okay.
Yes,
okay.
Yes,
thank
sir.
you. Okay, now I move on to another topic, that is electrochromic materials. So the word electrochromic can be divided into two, electro and chromic. You know the meaning of the word chromic, chromism, and so on. So even we human beings have what are known as chromosomes. It is the chromosomes, which give us the typical hair color, the typical eye color, and the typical skin color. Okay, the chromosomes. Okay, now so chrome means color. In other words, in the presence of an electric field, the color changes. Okay, so that is the characteristic of the unique characteristic of the so-called electrochromic materials. So electrochromism is defined as the ability of a material to change its optical properties. In other words, the color when a voltage is applied across it. And such materials are used in cathodes in lithium batteries, electrochrome layers in LCDs, etc. Smart gels. So these are polymeric materials. So these also undergo a shape change. In particular, they undergo a volume change, and the volume change that they undergo is enormous, tremendous. So these smart gels are also called engineered gels. That means the properties can be engineered, and so they can undergo a shape change to the extent of 100. They can shrink or they can swell by a factor of 100. So take for example, shape memory alloys. they do undergo a shape change. Okay, and the amount of strain that they undergo, the shape change, the amount of shape change they undergo is something like 5% in some cases. In the extreme case, you can think of some iron-based alloys, which exhibit something like 13%, that 13% being the highest. But in the case of smart gels, polymeric materials, we generally find that the the volume change occurs to the extent of 100. I mean, 100 times by a factor of 100. Okay, and in these cases, metal can be programmed to absorb or release fluids in response to almost any chemical or physical stimulus. So the figure here actually shows 4 different regions, and this actually correlates. I mean, the plot actually correlates the elastic modulus to the temperature. Okay, so there is a specific temperature called the TG, the glass transition temperature, and so in this region, there are, as I said earlier, there are 4 different zones that you can identify with respect to temperature in the case of such smart gels. So what are these areas? 1, glassy region, glass transition region, rubbery region, and fluid region, or the melting region. 4 different zones, and when it crosses this glass transition zone, it shows the maximum elastic modulus. It shows the maximum elastic modulus. So these are the characteristics of the so-called smart gels. Then let's also discuss some polymers which also come under what are called smart materials. Electroactive polymers. The acronym is EAPs. The first of the pioneering work in the area of electroactive polymers was initiated by a scientist by name Wilhelm Conrad Röntgen in the year 1980. And what was the work that he carried out, and what was the outcome? He actually worked on a strip of natural rubber measuring 16 centimeter by 100 centimeter, and he hung a weight to one end of the polymer, natural polymer, and he found that he subjected the strip to charging and discharging. Charging, that is passing electric current, and removing the electric current that was passed into it. So this actually caused a strain to be induced. Strain induced in a strip of 16 centimeter by 100 centimeter natural rubber with a fixed mass attached to the free end by charging and discharging. So such polymers are called electroactive polymers. From the 1990s, new polymers that respond to electrical stimulation with a shape or a size change have emerged. But then the beginning was in the year 1980 by the scientist by name Wilhelm. And in fact, I must tell you further that these electroactive polymers are also called artificial muscles. Why is it that they are called artificial muscles? Because these electroactive polymers have a behavior or properties which are similar to the biological muscles. And that's why the name artificial muscles. In fact, I can say about the application that these artificial muscles are used in robotics. Artificial muscles are used in robotics. Now, coming to the 2 different types of polymers, electroactive polymers. you can think of electric EAPs and ionic EAPs. There are distinct differences between the two. Let's look at the characteristics. In the case of the electric EAPs, you find that they are driven by an electric field. And in fact, the field that is required is very high, to the extent of 150 kV per mm. And in the case of the electric EAPs, you find that the response is much faster. And they also exhibit high mechanical density. On the other hand, in the case of the ionic EAPs, you find that they are driven by diffusion of atoms of ions and driven at a low voltage, that is 1 to 10 volts. Okay. Moving over to the polymeric smart materials, that is the electroactive polymers. We are discussing electroactive polymers. We just now identified two different types: electronic EAPs or electrical EAPs, and then ionic EAPs. So these electronic EAPs are basically dielectric EAPs, and they are also called ferroelectric polymers. I'm just highlighting some of the major things. And coming to the ionic electroactive polymers, you could also include the so-called conductive polymers under ionic electroactive polymers. Now coming to dielectric EAPs, so they have some distinct characteristics. That is low modulus, elastic modulus, and high dielectric constant. And these EAPs undergo a strain when subjected to an electrostatic field. And the so-called dielectric EAPs also have a different name, known by another name, and that is electrostatically restricted polymer actuators. Now coming to their behavior, they exhibit two distinct behavior. One, the strain that is induced is inversely proportional to the elastic modulus, E being the elastic modulus. And secondly, the strain that is induced is also related to the extent of magnitude of the electric field that is applied. In other words, the strain that is induced is proportional to the square of the electric field into the electric constant. And such dielectric EAPs are used in the artificial muscles of robotics. Then ferroelectric polymers, they possess spontaneous polarization that can be reoriented by applying an electric field. And here again, you can think of two different types, namely the piezoelectric polymers and electrostatic polymers. The electrostatic polymers could also be called electret polymers. And these are also used in the field of robotics as actuators and sensors. So please note that I drew your attention to the fact that they are used as artificial muscles. The reason as to why they are called artificial muscles is that they have properties that are akin to human beings, and that's why they're called artificial muscles. And different types of these polymers are used in robotics and micro-robotics in the form of actuators and sensors. Then optical fibers. I'm sure you are familiar with the optical fibers. So these are fibers that use change in intensity and phase or frequency or polarization modulation. So these are the inputs. So any smart material should have an input and an output. So now an optical fiber is a smart fiber. So this receives an input, and it, of course, it also gives rise to an output. So in terms of the input, so we can think of the intensity and phase, frequency, or polarization modulation. So all these could be changed. And these could give rise to a corresponding change in the strain, temperature, electrical or magnetic fields, pressure, and other measurable quantities. So we have seen that optical fibers are used in smart bridges. So this is actually science in action, technology in action. So in smart bridges, we make use of optical fibers. So you saw the pile deck, okay, the deck, okay, and you found that the optical fibers are being embedded. And what is the purpose? The purpose of the optical fibers is to, to know the load and other things. Okay. So actually, the optical fibers possess certain unique properties, and the properties do undergo a change when there is a change in terms of strain, temperature, electrical or magnetic fields, and pressure. So the table that is shown here illustrates the different variables and the methodology that is being used and the corresponding application in the context of the optical fiber. For example, the fiber composites embedded with optical fibers can detect mechanical loading and vibrations. So it is these are composites embedded with optical fibers. This can detect mechanical loading and vibrations. And what is the principle that is used? Photoelastic effect. Photoelastic effect. Moving over to the next one, the variable strain and methodology, change in optical power due to deformation. If you take an optical fiber, when it is deformed, okay, when it is deformed, when the dimensions change, the output that it gives rise to, okay, that is power or voltage that it gives rise to at the other end varies depending upon the deformation. So this is an indication of the strain that it has undergone. So by measuring the voltage, you can actually know the strain it has undergone. So applications, strain could be sensed in structures embedded with optical fibers. Next, temperature. So when an optical fiber is exposed to temperature, what happens? Its refractive index can change. That is, in a typical application, the part carrying an optical fiber is exposed to different temperatures. So at a lower temperature, it will have one refractive index. At a higher temperature, it will have a different refractive index. So by measuring the refractive index at the output, you will know the state of temperature of the structure. So the application, the thermal state of the fiber composites could be monitored by measuring the refractive index. This is science in action. This is technology in action. So optical fibers are used in smart bridges. They are used in many applications as well. Fullerenes. I'm sure you are familiar with carbon nanotubes. Similar to carbon nanotubes, you can think of fullerenes. So these are fullerenes are a form of carbon, or rather, these are spherically caged molecules with carbon atoms at the corners of a polyhedral structure. So as you can see, polyhedra. Carbon atoms at the corners of a polyhedral structure. Applications, there are many applications, but I have listed just one. Embedded into solid matters to enhance optical properties. Conducting polymers. Generally, we believe that polymers are insulators or non-conductors, but it's not true anymore because the 3 scientists from across the globe received the Nobel Prize in chemistry for the outstanding work, for the pioneering work in the area of conducting polymers. That means polymers can also conduct. So that means, so there are polymers that can conduct both heat and electricity. What is it that makes a polymer to conduct? How can generally polymers don't conduct? That's true. Why is it that polymers don't conduct? Because there are no free electrons. The electrons are locked in place. Okay, there are no free electrons. But then you can have what are known as conjugated polymers. So in the case, what are these conjugated polymers? So let's look at this here. So this is the structure of a conjugated polymer. What is so unique about this conjugated polymer? So you find alternating single and double bonds. Alternating single and double bonds. And what is the advantage of having such a unique bond structure? That is single bonds and double bonds alternating with each other. What is the advantage? So this actually helps in delocalization of electrons. In a conventional polymer, the electrons are confined to a particular atom. Okay, they are not free to move. So let us look at the other points pertaining to the conjugated polymers. Conjugated polymers have a unique chain structure. What is the uniqueness? The uniqueness lies in the fact that alternating single and double bonds in the polymer chain. And what is the result? The result is that the electrons are delocalized. Localized means being confined to a particular atom. Delocalized means they are free to move. So electrons are delocalized to the whole system, and many atoms share the electrons. So the electrons become charge carriers and conduct electricity. For the free flow of for this to happen, you need to carry out what is known as doping. That means you want to free the electrons which are confined to a particular atom. So to free the electron, you need to do what is known as doping. There are different ways of doping, like chemical doping and other kinds of doping. So there are certain elements that are used, for example, iodine and bromine, and which do serve the purpose. Okay. Now, any examples for conducting polymers? Yes, there are many. One of them stands out, polyaniline. So there is a polymer known as polyaniline. So this is a conducting polymer. That means it can conduct both heat and electricity. And this conductivity is made possible by doping, and the doping introduces single and double bonds, or that is delocalization of electrons. So the connecting polymers are used in very many important applications, especially in aircraft and spacecraft industry. In particular, in the aircraft industry, used as a coating to protect against corrosion. And in the spaceship industry, used in fuel cell systems. Okay, so if you're what do you call it? If you go to the outer space, okay, let's say there are some skylabs, so you need to have enough fuel. Okay, you need to have enough power. Okay, to go and come back, and it should also be lighter, and it should be free from any hazards. And that's why, we make use of fuel cells in spaceship industry. Okay, so here is a comparison. I have a few slides, and within about next 10 minutes, I think I'll finish it. I'll have to rush through that, but nevertheless, I'll do that. Connecting polymers. So here, certain characteristics are compared with respect to connecting polymers, metals, and insulators. So three different kinds of material conducting polymers. That is, usually we imagine or we think that polymers don't conduct. Our traditional understanding is that polymers don't conduct, but it is not true anymore. And our traditional understanding is that metals do conduct, yes, and the insulators don't conduct at all. Now, the actual conductivity of the three different kinds of materials expressed in Siemens per centimeter. In the first case, 10 power minus 11 to 10 power 3 Siemens per centimeter. Second one, 10 power 4 to 10 power 6, very high. And in the case of insulator, 10 power minus 20 to 10 power minus 12, very low. Now the carriers of current, electrons of conjugated double bonds. This is what I was talking to you about. So you create a condition whereby electrons can be made to move from one end of the molecule to the other end. Excuse me. And then metals, you know that in the case of metals, for conduction to take place, you must have valence electrons. Effect of impurity, there are other things, but I'll highlight a few things here. Impurities of only 0.1 to 1% can change the conductivity by 2 to 3 orders of magnitude in the case of conducting polymers. In contrast, in the case of metals, impurities do not have much of an effect. And in the case of insulators, they have a very strong effect. Connective polymers are used in different fields, and depending upon the particular characteristic that is being emphasized, the applications are brought under two groups, group 1 and group 2. Then shape memory materials. So these are materials with memory, and when it comes to shape memory materials, they exhibit two unique properties, namely shape memory effect and superelastic effect. And when it comes to shape memory materials, there are metals which exhibit this property, SMAs. There are polymers which exhibit this property called SMPs, polymers, or smart gels. Similarly, there are certain ceramics which exhibit this memory behavior. They are called shape memory ceramics. But as you go from metallic to polymeric to ceramic, the strain that they undergo decreases. And in the case of shape memory alloys, the reason as to why they exhibit this shape memory behavior is because of the occurrence of two transformations. One, austenite to martensite, and the reversal behavior of martensite turning into austenite. So this is what is responsible for the shape change in the case of shape memory alloys. I'll skip this. Okay. So coming to shape memory effect, so the material undergoes a shape change, okay, with respect to temperature, and the reason for this occurrence is the occurrence of the martensite to austenite and austenite to martensite transformations. So this is a schematic diagram which illustrates the relationship between shape change and temperature. Apart from shape memory effect, shape memory alloys also exhibit another phenomenon known as superelastic effect. This is also reflective of the memory behavior of shape memory alloys, but then it takes place at a higher temperature. In fact, the shape memory effect is called thermal memory effect, whereas the superelastic effect is called mechanical memory effect. Now looking at the mechanism of shape memory effect, so let us look at a crystal which or a material which exhibits shape memory effect. And let's say it is taken to a temperature in excess of AF. So there are four temperatures that are important in the context of any shape memory alloys. What are these? MS and MF, representing martensite start and martensite finish temperatures, and AS and AF, representing austenite start and austenite finish temperatures. In other words, when austenite is quenched, that is cooled faster, it can tend to form martensite. So here, initially, the material is in the austenitic condition. So usually, unlike in the case of steel, the austenite in shape memory alloys is usually referred to as beta. So please note the difference. The austenite, the high temperature phase, is usually referred to as beta at a temperature above AF. Now, when it is quenched, in fact, the right term to be used is quenched, it tends to form martensite. When does it form martensite? When it's quenched to below MF. In fact, this temperature should be MF, martensite finish. Now, so this one has a specific length, let's say L, and this one will also have this almost the same length. Why is it so? Because usually our understanding tells us that in the case of steel, when austenite is quenched to form martensite, it gives rise to change in length. It gives rise to change in volume. But in the case of shape memory alloys, the martensite which is formed is called thermoelastic martensite, a special form of martensite which does not give rise to any change in length. So this length is not any different from this length. Now, this martensite is deformed at a temperature below MF. Okay. Now, what happens? So this martensite is also called self-accommodating martensite. Self-accommodating martensite. So there are four variants: A, B, C, and D. A, B, C, and D. So they are all related to each other through fins. That's why these are called twin, self-accommodating twin-related variants A, B, C, D. And when the material is deformed below MF, it so happens that that particular variant, it could be A, B, C, and D. But here, it so happens that variant A is favorably oriented to the stress direction. So which grows at the expense of the other variants, B, C, D. That means A grows at the expense of B, C, and D. With the result that after the deformation is over, the entire volume will have only A variant, the predominant variant. And on heating it, you get what is known as the austenite. In other words, you get back the original shape. You get back the original length. And this is what is the mechanism behind the shape memory effect. And yeah, maybe I can show you just one slide. Maybe this, yeah. So a qualitative comparison of different smart technologies. We have, of course, come across different smart materials, but for the sake of comparison, only 3 distinct smart materials have been taken for analysis here, because even though there are many smart materials, these are used very extensively in practical applications. Okay, now coming to the driving force. Shape memory alloys, temperature. Magnetic materials, magnetic field. Piezoelectric materials, electric field. Materials, these are some of the examples. TANI, it's also known as nitinol, a very popular material, shape memory alloy. Then this one, TBFE, that's some terphenol. There's a metal called, an alloy called terphenol, terbium, okay, iron, and dysprosium. Okay, then PZT here, PZT and quartz. Advantages: shape memory alloys, large forces, high energy density, high material strength, high elasticity. So in the beginning, I said shape memory alloys are compared for 2 different properties. 1, the strains that they undergo, and 2, the forces that they generate. So you find that shape memory alloys can produce large forces. And secondly, in the case of macroscopic materials, some of the advantages: high frequencies, high temperature range. Piezoelectric materials, high bandwidth, high frequencies, low power actuation. Limitations of shape memory alloys. There are many, but I would say high hysteresis, then limited temperature range. Here again, in the context of macroscopic materials, many are listed, but I would say limited strains and brittleness, typically brittle materials. Moving over to piezoelectric materials, limited strains, typically brittle materials. So that's all I can share with you as of now for want of time. And so I'm done. And
Sir, so good afternoon, sir.
good afternoon. Yeah.
I think you have covered. You still want to cover, sir?
It's okay. I think.
Many are faculty members, sir. They are going back to their homes.
Okay. Well, yeah, I'll finish. I mean, I'm done. I finished. Yeah.
Finish, sir. Please don't mind, sir. Actually, all are working, sir.
Okay, okay, no
So
problem. Yeah,
all are
yeah,
mainly in private college, so they will be
understand. Yeah,
going to their homes, sir. So, sir, thank you so much, sir.
yeah, welcome. Yeah,
Sir, thank you so much, sir. You have covered a wide variety of smart materials, sir, and you have covered smart structures and smart bridges, piezoelectric materials, electrostatic materials, magnetostrict materials, electrostick materials, so many which we didn't hear about us. It was a very new area for us, and we are happy that you have given the interview to you, sir. You have taken a lot of time to explain with so much pain. You have about 2 hours. You have explained very well, sir.
thank
The
you. Thank you.
introduction was really good. Our participants are also very happy,
Thank you.
and some
Thank
of
you.
them don't want
Yeah.
still want more.
Yes.
Because of you still want,
Yeah,
sir,
it is.
Venkatesh, sir.
Yes, madam. Yes, madam. It is very elaborative and extensive lecture. In fact, it will be very difficult to go through so many books. So
Yes,
after going through these slides, yes, we'll have a broader idea, and we can suggest our students like undergraduates based on this information, their projects and other things, whatever, some new ideas. Then if we have broader this thing within short period of whatever 1.5 or 2 hours, sir has gave broader information and idea. It takes so many hours if we refer book. It is very difficult to even catch all this information in a textbooks, text or whatever
thank you. Yeah.
literature, sir. Thank you so much.
May I know your name? May I
Sir,
know your name
I
and
am K.
what you?
Venkateshwar.
No.
Yeah, yeah, sir. I am K. Venkateshwar, working with the Mechanical Engineering Department, OU College of Engineering, sir.
Okay.
Working as
He is my
assistant
colleague,
professor.
sir.
Yeah,
Okay.
assistant
Okay.
professor on contract for the last
Oh,
14 years.
oh, oh, this is very
This is my,
strange.
this is my 15th years of service.
Oh, no. I think they should do.
But that is pure
They should,
mechanical, no, sir. That is all pure
yeah.
mechanical, whereas this is, yeah.
Okay.
Yeah.
Yeah, and
Thank you, sir.
actually, yeah, I think initially I took lots of time. Maybe I should
No,
have
no,
cut
not
short.
like that.
No, sir.
Mm,
Actually,
Not
it's
like that.
very good.
Yeah.
Yeah, yeah. Uh,
Uh,
because
you,
I identified only some 75 slides, but by
yes.
the time I finished 90 minutes, I covered only about 35 slides, even after some 90 minutes. So I don't know where I went wrong. But anyway, in the interest of the participants, I took extra time to explain each and every word so that
Yes.
the principles and the mechanisms are understood thoroughly. So that was the noble objective that I had, noble idea that I had. And that's why I spent more time. And
Yes, sir. For
yeah,
beginners, it is required.
yeah,
So that the ideas or otherwise the material will be clarified.
yeah,
For beginners, yes, it is required. That much explanation is required,
yeah,
and
yeah.
we will be very thankful if you can, allow us to have some slides, if not entire,
Okay.
or otherwise in a nutshell
Yes.
form at least.
Yeah. Okay. I will send a PPT. Okay. I will be
Yes,
very selective.
yes, sir.
Most important slides I will share with you.
At least, sir. Yes, please, sir.
Yeah,
Please.
I'll share with you the most important slides. And yeah, that's all. And,
Thank you so much, Professor. This is if any questions, then I think we can take mail from Madam, and
yeah,
later
okay.
Also.
Sure.
I
What
think
about the
we can
other? What about
interact.
the? Yeah, very nice. What about the other speakers? They were sticking to time, or they overshot the time.
Took time in the sense they may have less slides, so that based on the allotment of time. But for smart materials, this is required, sir. This is it is required. In fact, If it is in the morning session, we will be having utilized full-fledged time
Okay.
up to 1:30 like that.
Okay. Yeah, I'm really happy.
Yes,
Yeah.
Yeah, wow, madam, what madam said is right. In the evening, people working with some engineering college outside Hyderabad, they are in a hurry to come back to the city.
Okay.
So they
No
have to
problem.
catch their college bus and person. Yes. Yeah.
Okay. I know
That is
that.
why.
Okay. Yeah. Anyway,
Yeah.
thank you so much for the nice feedback, positive feedback. I'm really happy that whatever time I've spent has been really beneficial to you. Okay.
Yes,
So,
sir. In fact, we will be very thankful to you, sir,
thank
having
you.
such a nice lecture.
Yeah.
Yeah, that's why we request you to go for some extended hour. Otherwise, otherwise, naturally, people will be okay. Yeah, it is very nice lecture, sir.
Thank you.
Thanks for the organizers also. And
thank you. Yeah. Okay. Yeah. Okay. Fine. So.
Thank
Then,
you so much. You
Yeah.
have taken a
Welcome.
lot of pains to explain.
Yeah.
From starting from basics, you have explained, sir.
Yeah.
Thank you very
It's my
much.
pleasure. Yeah. Welcome. You're welcome. Anytime, you can call me again. Now, because
yes.
I thought, I would be able to cover all the 75 slides maybe in about an hour and a half, if not an hour and a half, at least in 2 hours. But even after 2 hours, I find that I'm still left with a few more slides. It doesn't matter. Maybe in the future. Okay. The future, we can always look up to the future with a hope. Yeah.
Yes,
Yeah,
so
sure.
thank you so much. And then, okay.
Thank
so,
you.
Okay. So then I'll log off now.
Yes, sir. Thank you so much, sir. Thank you, sir.
Welcome.
Thank you for a very good lecture. And
yeah, thank you. I'm logging off.
Thank you for accepting, sir. Thank you, sir.
Thank you.
We had a very good talk. Thank you so much.
Thank you, sir.
Welcome,
Thank you.
Welcome.